Hello, my name is Aiden Dosh, and today I'm going to be talking about the physics of trebuchets. The trebuchet was developed in China between the 5th and 3rd centuries BCE as a heavy artillery piece for destroying fortifications. From China, it steadily moved west, reaching the Mediterranean by 500, then on to Europe. Due to its long range, the trebuchet augmented or replaced earlier forms of catapults and was a staple of siege warfare for hundreds of years until the rise of effective cannons. There are two main types of trebuchet, the traction and the counterweight. Both use a beam with the pivot point towards one end. On the longer end of the beam is a sling attached to the projectile, usually a large stone. For traction trebuchets, a team of soldiers pull ropes attached to the shorter end of the beam to launch a projectile. The counterweight trebuchet was developed later, and instead of being pulled, the smaller end of the beam has a weight attached to it, and it uses a force of gravity to launch the projectile. The two types of trebuchets I will be focusing on are the seesaw and hinged counterweight trebuchets. Both are examples of a counterweight trebuchet. Both models omit the sling for simplification, and instead the projectile will be resting on the long end of the massless beam. The seesaw trebuchet has the counterweight attached directly to the short end of the beam, whereas the hinged counterweight trebuchet has a hinge on the end of the shorter beam, attached to another beam whose other end is attached to the counterweight. The question we will explore is, how do the two models of trebuchet work? What forces are acting on the trebuchets? What are their kinetic and potential energies? We will also be looking at whether the ranges for the two types of trebuchet are different, and if so, why. First, we will look at the forces acting on the simpler seesaw trebuchet. The only force acting upon this trebuchet is the force of gravity, which pulls down with a strength of m1 times g on the counterweight and m2 times g on the projectile. The mass of the counterweight is much greater than the projectiles, thus creating torque around the pivot point in the clockwise direction. The counterweight will drop from an angle of 3 pi over 4 to pi over 4, at which time the projectile will be launched at an angle of pi over 4 from the ground with a velocity of v1. Initially, all the energy for the seesaw trebuchet will be gravitational potential energy. The formula for gravitational potential energy is mass times gravity times height. We simply add the mgh of the counterweight to the mgh of the projectile to get our total initial energy. As the counterweight swings down, the potential energy will be transferred to rotational kinetic energy, which is equal to 1/2 the moment of inertia times the angular velocity squared. Like the potential energy, we simply add up the kinetic energies of the two masses. The moment of inertia for the counterweight being I1 and a moment of inertia of I2 for the projectile. For the hinged counterweight trebuchet, the force of gravity will be the only force acting on it. Like the seesaw, the gravitational force will be m1 times g on the counterweight and m2 times g on the projectile. With mass 1 being much greater than mass 2, the counterweight will drop from an angle of 3 pi over 4 to pi over 4, thus creating a clockwise torque on the central pivot point. While the counterweight drops, it will pivot about the hinge on the small arm, keeping the counterweight vertical. The velocity of the projectile upon release will be v2. Before the counterweight is released, all the trebuchet's energy is gravitational potential energy. Again, as the counterweight drops, some of the gravitational potential energy will be transferred to kinetic energy. However, with this trebuchet, the moment of inertia for the counterweight will not depend on the length of the smaller beam, L1, but it will instead depend on the distance between the central pivot point and the center of mass of the counterweight, as denoted by the dashed line. This length, L4, will be constantly changing as the counterweight drops and will give us the new moment of inertia, I4, for the counterweight. Here is a plot of the trajectory of the projectile after it is launched by the seesaw trebuchet. The trajectory is in the shape of an arc with a constant velocity in the x direction until the projectile is eventually pulled to the ground by gravity. To find the range of the two trebuchets, we will first need to find their angular velocities when the angle between the stand and the short end of the beam equals pi over 4. We can find this by solving for the final angular velocities from the equations of motion of each trebuchet. To convert from angular velocity to velocity, we simply multiply the angular velocity by the radius, which in our case is L2 for both trebuchets. The velocity can be split into its x and y components using trigonometry. Using the velocity in the y direction and the acceleration due to gravity, you can find how long it takes for the projectile to hit the ground. Multiplying this time by the velocity in the x direction gives you the range of the trebuchet. Using different values for L3 while keeping everything else constant, change the range of the trebuchet. When L3 is 0, the trebuchet is a seesaw and has a shorter range than a counterweight trebuchet with a short L3, such as when L3 equals 0.25 meters. However, as L3 continues to increase, the range starts to drop. When L3 equals 1 meter, the range has dropped to much shorter than that of the seesaw trebuchet. Why does the length of L3 affect the range of the trebuchet? The decrease in the gravitational potential energy is equal to the increase in the kinetic energy. If the kinetic energy starts at 0, that means the final kinetic energy when the projectile is released is equal and opposite to the change in gravitational potential energy. Because the short beam and the attached counterweight are always dropping by the same angle, the change in height and thus the gravitational potential energy are changing by the same amount no matter the length of L3, even if they have different initial and final heights. If the change in potential energy is the same, then the final kinetic energy for all trebuchets is a constant. If the kinetic energy is equal to 1/2 of the moment of inertia times the angular velocity squared, then as the moment of inertia decreases, the angular speed, and thus velocity v, increases to keep kinetic energy constant. The moment of inertia for this problem equals mass times r squared. If the mass is m1 for all trebuchets, then the only changing variable for the moment of inertia is r, which in this case is L4. L4 is directly related to the length of L3, so the smaller the L3, the smaller the L4. A smaller L4 means a smaller moment of inertia and a greater angular velocity and thus greater range.